Okay, now I want to talk about quantification and binding of variables with the issue of n-ary propositional functions. So an example of a two-ary would be like p of x, and xy has some predicate p. On the other hand, we could go to, say, three-ary if we wanted to, and say, for example, q of x, y, z, and let's do a specific example, say like x squared plus y squared is equal to z squared, right? So this would be evaluate the true or not true, and we would look at this, and again we have this idea of what's the natural domain, what's the restricted domain, and so we could restrict ourselves to, say, just the non-negative ends, say 0, 1 to infinity, positive ends 1 to infinity, and the idea of finding solutions to particular problems. And when we have things like this, it's not that bad of an issue when we look at it and we just simply bind it, and we bind it through evaluation. So we've done this one before. We could say things like q of 3, 4, and 5 is true, right? We just simply plug 3, 4, and 5. 3 squared plus 4 squared is 5 squared, and so it evaluates the true. And so we could just plug particular numbers in. On the other hand, we could bind by evaluation, say, with quantification. And say, we could say things like, it is not the case that there exists x such that q of 1, 1, x, where obviously for the universe of discourse, so we were looking for integers, and so what we're really saying here on this particular thing is this is actually saying that there is no integer such that, well, 1 goes here, makes 1 squared is 1, 1 squared is 1, so it's such that 2 is equal to, let's call it integer x, such that 2 is equal to x squared. So no integer squared is equal to 2, right? It's actually no rational. And this is true as well, and so, you know, whether we could prove things or not, so we can bind particular things. The problem is that what happens when we start to bind a couple of variables, and does the order of the binding matter? So let's try another example, and let's say that love square triangle denotes that square loves triangle, and I'm going to pick a universe of discourse for square to be, say, people, and the universe of discourse for the triangle to be, say, classes. So this is the idea of something, groups of people loving, or individuals, humans loving particular classes that they're taking. And so whatever goes into this position is from here, which is from this universe of discourse. So whatever goes in the first position must be a person. Whichever goes into the second position, which then eventually moves here, is going to have to be a class of a particular sort. And so what I want to look at here is what would happen if I would bind, say, for all people, for all classes, did I use capital L on that? Yep. Love PC. What would that mean, right? And so why am I saying people and classes? Because I knew I was going to put the P in the person position, and I knew I was going to put the C in the position of classes. So I picked P and C because, well, works well. And that's the idea of picking variable names or different things that actually help you read the problem. And on the other hand, what would happen if I would, you know, still use the P is still people and C in that order, but what would happen if I would switch the order of binding? I bind all people, I bind people to everyone in this set, and then I bind classes to everyone in the entire universe of discourse. But what if I would bind classes before I did people? What happens if I would say take some people and then bind all classes, and then again, would it matter if I would switch the order here? Or what if I would bind existentially both of them at the same time? Would that matter if I would switch the order of binding for some class and then binding for some person and then the predicate? And we'll look at this and ask, for example, like go through here and ask when this is true. So for this particular problem, like on the first one, I would say, all right, for all people, and when you look at this, it's easiest to think of this, especially when we have two, to go through here and say, look at it as a spreadsheet, like person 2, person 1, person 2, person 3, etc., class 1, class 2, class 3, etc. And then we can go through here and start to compare. And so what does this say? This says for all people, right? So the first thing I do is I'm going to look at all of the people. Then I'm going to move on and say, okay, for all classes. And then I'm going to, oh wait, now I have to look at all classes at the same time. And so for all people, for all classes, that means I'm looking at this entire spreadsheet and a bunch of cells, right? So you could write this all as cells if we want. Same way here. So we have a spreadsheet with all these cells. And so all of them, I'd be considering them and saying that the person loves the class. So what you're saying is for every person, they love every class. So as I go across and handle everybody, they're going to love every class. It's going to, oh, love, love, love. Person 1 loves all these classes. Person 2 loves all these classes. Person 3 loves all these classes. And so this entire spreadsheet is filled with nothing but the fact that they love all these classes. Compare the second one. What it says is for all the classes, first I'm going to look through the classes and then I'm going to compare the people. And I'm going to notice that for all people, that the people love that class. So that means for class 1, I found that person 1 loved it, person 2 loved it, person 3 loved it, etc. And then I moved into the next class. Oh, everybody loves that one as well. Move to the next. Everybody loves that as well. In the end, it's just going to fill it up. So it looks like for all, whether I say person 1 loves all the classes, person 2 loves all the classes, which is what this says, or the second one, which says, well, for class 1, everybody loves it, and class 2, everybody loves it. It ends up being that they both would meet the same thing. It just shows that everybody loves everything. And so in English, this would simply be all people love all classes, which is the same thing as all classes are loved by all people. So it ends up that these two are logically equivalent. Now, let's go to the bottom as well and do the same sort of concept and ask, well, what does that look like? And I'm going to consider these two. Well, the first says there's some person, so I'm going along the people, and I found, say, some person. And then as I look at the classes, there's some class that they love. And so let's say person 3 ends up loving class 2. And so, oh, look, I found it. Right now, there might be more than one person with classes that they love, but there's at least one, right? There's at least one person with at least one class it loves. And if I would have loves in different places, you know, that would be true still. Well, person 2 loves this class. Well, person 3 also loves class 3. So it occurs at least once. So the first says, look at the people and then find the specific at least one class that they love, and there's at least one person with at least one class. The second one says, let's look at the classes and then check. Well, class 1 doesn't have anybody that loves it. Class 2, oh, that's loved by person 3. And class 3 is loved by person 2 and person 3. Well, if this, when is this true? Well, when there's at least one L in the entire set, and it will find it. When is this true? When there's at least one L in the entire spreadsheet, and this will find the exact same ones. So it really doesn't matter. You know, these are logically the same. And what they say is some person loves some class, right? There's a person who loves some class, you know, of all the people in all the classes. And there's a class that somebody loves means the same thing. So it works out pretty well. Now, the middle one, on the other hand, are going to end up not being the same. So these are logically equivalent. These are logically equivalent, but the bottom are not. I mean, sorry, the middle two are not. It ends up for the middle two that these, so that would be like type 1, type 2, but 3 and 4 are going to be different from each other. So how would this work? So 3 says there exists some person that for all classes, that person loves it. And so 3 would find a special person that would love every class, and so there's an L's, all L's in a vertical column. And so that's what this one finds, some person that loves every class. On the other hand, what does, it's not erasing nicely today. What does number 4? Number 4 says, for all classes, so for every class, there's a person somewhere that loves it. So for class 1, maybe person 1 loves it. For class 2, well, maybe it's person 3. For class 3, well, maybe that one's person 3. And say for class 4, well, maybe that's person 2. So what 4 says is every row has a person, right? Has an L in every row, whether they're vertical or not. There's an L, like class 1 has a person, class 2 has a person, class 3 has a person, class 4. For all classes, they have a person. These are not the same. Now, 3, if 3 is true, 4 is also true. But if 4 is true, 3 is not necessarily. So they're not true and false in the exact same features. And they're they're somewhat different from each other. But I might as well just simply say they're different. So one of the easiest ways to do these sorts of binding, it ends up being that if everyone is universal or if everyone is existential, order of binding does not matter. They're going to be logically equivalent. If you mix existential and universal, order very much matters. It matters a lot, and you're going to have to think about it. And one of the easier ways to think about it is to usually, if it's 2 of them, to kind of spreadsheet it, or at least keep your mind in it. If there's 3 of them, it's no longer a 2-dimensional spreadsheet, it's like a 3-dimensional spreadsheet. So as you go through things of this nature, you can use these sorts of visualization to kind of dig through and ask, when is this true and when is this false? Along with having these nested quantifiers, negation properties still hold, right? So for negation, we still have the same ones, that if I would negate a universal, it's the same thing as an existential negate the predicate. And if I would negate an existential, it's the same thing as a universal with the negation of the predicate. But that now allows us to simply say, okay, so for example, what would happen if I have, it's not the case that for all x, there exists a y, there exists a z of q, x, y, z. If I want to take this negation through, I would take it through the first. This all becomes an existential. Take it through the next, the existential becomes an all. Take it through the next, the existential becomes an all. And so we would say that this is simply just flip everybody. Existential, universal, universal, existential, and it's not the predicate. And the last example of the textbook goes through like the limit definition of the derivatives and takes a negation through it to talk about it. And that's a good one to read as well, to go through it. But in particular, we now, I mean, you sit there and you look at this and say, I just don't get to rearrange things. Once we start to mix, if you mix, you're going to have to leave it in the form that you see it in terms of, could I just start taking things and let's take this one and move it. No, you don't get to, right? So if everybody's universal or everybody's existential, you can leave it alone. If it's not, if they're mixed, leave it. You're going to have to take it as you see it and discuss what it is as you work with it. All right, so the next thing we're going to do is take some examples of English and symbols and actually do some particular examples.